About a year ago, the chief operating officer at Bloom Energy came to speak with me, and he said that we're having a problem with our incoming quality control procedures. They were taking too long, they were costing too much money to do, they're involving too many people, we didn't have the resources, they required more and more equipment. And you've got to understand that in the fuel cell manufacturing area, what we use is a lot of plates. They're about 4 inches by 4 inches in size right now, although they're getting bigger. A typical Bloom box contains about almost 10,000 plates. And then we have 6 boxes in a Catalina system that'll generate about 200 kilowatts of electricity. And the inspection procedures involve taking these samples, the plates that came in from several manufacturers, and measuring about 46 different critical to quality parameters on it. And each one of those involves specific measurements. So they were using what was called attribute sampling, basically taking a specified sample size, in this case 80, randomly selected from each batch that came in, and these critical to quality measurements were measured and they were compared to the specification limits. And if the samples didn't meet the specification limits, they were considered defective. They were allowing 0 rejects out of a sample of size 80. And if they were rejected, then the whole the whole batch would be inspected. If you take a look at generating what we call an operating characteristic curve based on a sample size of 80 and an acceptance number of 0, you end up with a curve that looks like this over here. And this is called an operating characteristic curve. The bottom axis is basically the incoming percent defective in that sample. The vertical axis is the probability of accepting the product. So you can see that product that comes in at very low defect levels has a high probability of acceptance, and product that comes in at higher levels of defects will have a low probability of acceptance. In particular, 2 points on the curve are often referenced. One is the 95% acceptance point, which we call the AQL, which is an acceptable quality level. Obviously, if the defect levels are coming in low, you would like to accept that product a lot and use it in production. On the other hand, the 10% probability of acceptance or 90% probability of rejection is called the RQL, rejectable quality level. And at that point, you'd have to reject the product a great deal of time. And that level corresponds to about 2.84%, whereas the acceptable quality level is very low, 0.064%. And there's a midpoint over there that's about 50% probability of acceptance. That's about 0.86%. If you multiply if you multiply the probability of acceptance times the percent defective, you generate what we call an AOQ curve. Okay, that's an average outgoing quality curve, and it peaks. And it peaks because when the quality coming in is very good, you accept it a lot. On the other hand, when the quality coming in gets bad, you go over that peak and you end up rejecting a lot of the lots and you end up rescreening. And the assumption is that when you rescreen, you inspect every single piece in the lot, and therefore you get low, outgoing, you get very good outgoing quality from that. In this case, the average outgoing quality limit corresponds to about 0.5%, 0.46%. The proposal that I considered when the COO asked me was instead to employ variable sampling plans, and they would result in a significant reduction in the sample size requirements compared to the attribute sampling plan, while providing equivalent protection against bad batches. Now, you've got to realize that every single part was being measured in this sample, and they were physically taking measurements. So they were changing very valuable variables type data into attributes data. And that's always, to me, a no-no when you're in industry, is to take good variables type data and change it into something that just basically go, no go, in and out, so forth. And the point that I was making to the incoming quality people is that if you're actually measuring a continuous parameter, you have very much more information than just simple counts of defective parts. And if you can estimate the mean and the standard deviation of an assumed distribution from the samples that you're actually measuring, you can estimate the percent defective relative to the specification limit quite accurately. So if I know, for example, I take a small sample and my sample mean and my sample standard deviation push me far out away from the specification limit, I do not need a large sample to prove that I'm not going to have very many defectives in that sample. On the other hand, when I get close to the spec limit, in this case we're treating it as lower spec limit, I would like to have a large sample size if I'm going to prove that my defect levels are very, very low. So the whole idea is take a small sample, measure it, and then do a projection as to what my defect levels would be based on that small sample. And if it's good enough, then I don't look at the remaining samples and I accept the batch. So in a variable sampling plan, it's possible to obtain equivalent or better discrimination power, even with smaller sample sizes, than when using variables data, when using attributes, count, pass, fail, go, no, go, or in-spec, out-of-spec type data. Now, variable sampling plan requires knowledge of the type of distribution. Generally, we assume that it's normal, but I'm going to show you some cases where that isn't exactly the case. And the standard deviation, how do I get the standard deviation? Well, I'm going to use historical data since we already have that data on, say, the last 20 lots. And I'm going to estimate the standard deviation based on the most recent lots. So when we have acceptance sampling by variables, for each of the critical to quality measurements that we take based on the estimated, and now we're going to assume known, because we're going to estimate it from the previous 20 lots standard deviation, the specification limits, the acceptable quality level and rejectable quality level proportions that are defective, that are acceptable and rejectable. And then we're also going to put an alpha and a beta, which is the producer's risk. The producer's risk is the probability of rejecting good product, and the consumer's risk is the probability of accepting bad product. And we're going to determine a sample size and an acceptance mean, K. So the whole idea is for a lower spec limit, for example, if the average of a small number of units is equal to or above K, then the CTQ passes and we don't do any further measurements. If for an upper spec limit, if the average of the K is, or the sample is below K, then the CTQ passes. If the average of the sample mean is below K for a lower spec limit or above K for an upper spec limit, then the batch fails for the CTQ and they'll have to screen. And they always had to fall back on. If they took a small sample of size 5 and they rejected a lot, they could go back to their attribute sampling, the sample of size 80, and wouldn't lose anything. Now, if you have two-sided limits, you'll have a K upper and a K lower. And if the average of the two limits is outside, the K upper and the K lower, then you'd reject a lot. If it's between them, you would accept it. And as I say, you can always rescreen based on the previous acceptance criteria if you do reject a batch. So here are the steps in variable sampling for single-sided lower spec limit. We're going to estimate the pool standard deviation from 20 recent lots. We'll determine the desirable AQL mean, we'll call it mu-A, corresponding to the specified acceptance proportion defective PA. So what we're going to do is find out what mean from a normal distribution with a known standard deviation will give us that defect level that would be acceptable 95% of the time. And then we're going to also determine the undesirable mean, we'll call that mu-R, corresponding to a specified rejectable proportion, level PR. Then we'll use that of the current attribute sampling plan of 2.84 as the determination of the percent allowed to the rejectable mean. Then we're also going to specify the producer's risk of rejecting a batch if the true mean is the desirable mean, and that will be about 5%, alpha 5%. And then we'll also specify the risk, the consumer's risk, of accepting a batch if the true mean is the undesirable mean. That's typically, we're going to have that at about 10%. These formulas show you how to calculate the sample size. These formulas are derived in Schilling's book. It's referenced at the end. They're also derived in Burr's book, Quality Control. You can see that the formula for the sample size depends strictly on the alpha-beta risk and the difference between the standard normal variates for the rejectable and the acceptable quality levels. And then the K formula is based on putting those together with the lower spec limit and then using the sigma that's in there. So the plan is if the mean of n items is below K, we'll reject the batch. If the mean of n items is greater than K, we'll accept the batch for a lower spec limit. And if the batch is rejected, go back to the original attribute sampling plan. Now, it's important to periodically verify that the measurement system analysis, what we call that gauge R&R, has been performed on the tools used to measure the CTQs. This was critical to make sure that we had consistent tools that were measuring the CTQs very accurately. You want your tools to have a measurement error that's small relative to the differences that you're seeing in the product. I strongly recommend what's called the measurement system analysis that's been implemented in JUMP based on the work done by Don Wheeler, evaluating the measurement process. It's far superior and actually makes more sense than the AIAG, the Automotive Industry Association Group proposals. And I don't know if you've ever struggled with that issue where you start adding different components of gauge R&R to appraisal R&R and the numbers that don't add up to 100%. Don Wheeler's analysis methodology solves that issue. Here's one example. In this case, we're measuring the X dimension on the product using JUMP's MSA analysis. And it showed that this measurement was first class. Basically, the measurement error was less than 10% of the total variation. And in fact, in this case, it showed that you can see the components of variance, which is the far better way of looking at the data, that 99.3% of the total variation was product variation, product to product, rather than the measurement associated with the tools. Now, here's actual data from the most recent 20 batches. Each one of those vertical areas, vertical lines, represents 80 measurement data points. You can see that 4 samples are close to the lower spec limit of 100.15. On the right-hand side, this is displayed obviously in JUMP using the fit Y by X platform. And to the right, you can fit CDF, cumulative distribution functions, to each one of the data groups. And you can also compare the density. JUMP's got a very nice overlaying ability to do the density analysis in the lower right-hand corner. You can compare the densities. They're fairly close, but you can see some of those are coming close to a lower spec limit. The next thing to do is take the recent 20 batches and take a look at what the actual distributions look like using the distribution platform in JUMP. And we noticed that 3 X dimension batches close to the lowest LSL have standard deviations that are smaller than the batches furthest from the LSL. This, to me, indicated possible bias, truncation in the measurements. And when you try to find the source of this bias, there are 2 possible sources of the bias. Number one, the vendor supplying the product realizes that he's coming close to a lower spec limit and actually screens the product before you get it. Another thing that I found out in working in industry is that technicians who take the measurements do not like to get rejects in their measurements because they somehow or other feel that they're causing it. So they may end up loosening the tool as they get to the measurements so that they have fewer and fewer parts that are outside of specification. And we'll see that these distributions actually do not appear normal. And we've emphasized that with the technicians that are making the measurements to be accurate with the measurements, but this is something that happens in industry, and unless you've actually gone in there physically observed them, you don't realize that this can happen, and you can get measurements that are, when they get near the reject level, the lower spec limits, they tend to put a little bias in it. So to estimate sigma, use the data from the most recent 20 batches. However, if we're going to take data from the most recent 20 batches, we have to verify that the process is stable. And that is to verify that the batch-to-batch means reflects a stable process with no out-of-control signals in the individual's chart. Now, why do we use individual's control chart in this situation? I mentioned batch-to-batch type variation. Well, the variance within a batch is much more consistent than the variance from batch to batch. And if you try to set up control limits based on the within variance of a batch, you'll get control limits that are very, very tight, and you'll end up thinking you have a total process that's out of control. So what we do in this case is we take individual measurements, the mean of the batch, and we'll use that as an indication of the stability of the process. If that's the case, the process is stable, then you can pool the 20 variance estimates from each one of the individual batches together to form a pooled standard deviation using this formula over here. So here's the data on the X dimensions, the control chart. This is individuals plotting of the control charts, IR chart. The individual averages are on the top chart, the ranges are on the bottom, and you can see that the process is stable for batch-to-batch type variability. So we felt comfortable using an estimate of the standard deviation from these 20 batches, and then we consider that as a known standard deviation at that point in time. This is the way it's set up in the formula set up in JUMP. Again, the formula on the lower left-hand side gives you the batch pool standard deviation in JUMP, a very simple formula to apply for each one of the data points that we have over there. Each one of those rows is basically a batch. And we have the mean for each batch. We can also look at the standard deviation that we would pool, and the pool standard deviation is shown. Now, the other thing that you'd like to do in this kind of a situation is verify that the process is normally distributed, the data is normally distributed, because that's the assumption under which we derive those formulas for the sample size and the k-values. JUMP has several reports that can be used to check normality. A simple analysis can be done using JUMP's distribution platform by selecting the normal quantile plot for the CTQ measurement. And if the data points fall in a straight line, then the normal assumption is something that we would consider to be reasonable. And you can see over here, here's the data from several of the batches, 2 batches over here. And these batches, again, had some means that were some distance from the lower spec limit. And as far as we can tell, you know, the normal distribution is a perfectly reasonable assumption for this data. What got interesting is when we started getting batches that were close to the specification limit. And you can see that the mean of this batch over here, the spec limit is 100.15, and this is 100.179. It's close to the lower spec limit, and the histogram appears now to be right skewed, as you can see from the lower histogram on the bottom. So a normal distribution with this estimated mean and sigma predicts 10% of the, roughly about 11% of the readings should be outside the lower spec limit, and the actual number was 0. Okay, so this probability of 0 occurrences out of 80 is very rare. You know, 1 chance out of 10,000, basically, indicating an extremely rare event. And this is where we got into questions about truncation below the lower spec limits, or that the operators were adjusting the readings to get them all within specification and not end up having any rejects. So it's something you just have to be aware of when you're applying these kinds of sampling plans. If you have the data, to take a look at them to check the assumptions for reasonableness. So here's the actual process now. We said the lower spec limit on the X dimension is 100.15. The AOQL percent defective that we had from the variables, from the attribute sampling plan was 0.064%. For a normal distribution, that equates to a mean of 100.23 based on the sigma that we estimated from the 20 lots. And the formula to estimate the mean can be easily derived in an Excel function. You can see the norm SINV of that defect level is 3.22. That gives you the standard normal variant, multiply it times the standard deviation, and add it to the lower spec limit, and you come up with 100.23. So basically, the k-value that we're going to use as protection for AQL is 100.23. A normal distribution with a mean of 100.23 and a sigma of 0.0252 will have 0.064% of the values below the lower spec limit. Now, we also need to find the RQL value. The RQL percent defective, we had 2.84. We go through the formula again. We calculate a z-value of 1.905, and that turns into 100.198. So basically what this series of calculations shows is that a normal distribution with a mean of 100.198 and a sigma of 0.0252 will have about 2.84% of the values below the lower spec limit. Once we have those, then we can plug them into the formula and calculate the sample size. Now let me make sure that we understand visually what we're talking about over here. We have a lower spec limit shown as the blue dotted line, and we have over here a red curve which stands for the distribution, the normal distribution, which has a mean at the unacceptable or the rejectable quality level. And you can see if we have a mean at that value UR, that will end up with about 2.84% of our product over here in the lower left-hand corner being outside the specification limit. On the other hand, if we have our mean at mu A, then we'll have only about 0.0064% of the product outside of the specification limit. Now, the other factor we have to think about is obviously the alpha beta risk. Here's the formula in which we plug in the z values for the acceptable, rejectable quality level and the alpha beta risk, and it comes out to about 5. So instead of taking a sample size of 80, we're going to take a sample size of 5, and then we determine K from the formula. It ends out being 100.2125. So the plan is very simple. If the average of 5 items is less than 100.25, we're going to reject the lot. If the mean of 5 items is greater than 100.215, we'll accept the batch. And then if the batch is rejected, we go back to attribute sampling. Now here's the explanation of the alpha and beta risk over here. And basically, again, lower spec limit in blue. K is the value at 100.2125. And if we have the actual true distribution at mu alpha, but we end up measuring it at mu alpha, there is a risk. There's an alpha risk that we can reject the product. So here's a case where the true mean is at mu alpha, but because there's a certain risk that the distribution, the black curve over there, will fall below K, that's the risk of rejecting good product. On the other hand, we could also have a mean mu A, shown in red over here. And when we measure the distribution of the sample of 5, that's the narrower normal distribution shown in black over there, there is a risk, beta risk, that we could have it be above that K value, and we end up accepting bad product. Okay, so that's how the alpha and beta risks are portrayed to do the actual calculations for generating the sample size and the K values. So here's now the comparison between a sample of size 5 versus a attributes data of 80 and accept on 0. And you can see that the lower left-hand side is in terms of the incoming percent defective, and the right-hand side is in terms of the incoming means. They're both equivalent curves. It's just different representations of the two acceptance procedures. Both of these curves have the same probability of acceptance at the AQL, 95%, and the same probability of rejection at RQL. And you can see that the variable sampling plan is a little bit tighter. Okay, that's the red curve shown on the left over here, and also relative to the mean over here. So, for example, you can see that at the 50% point that the attribute sampling plan would accept about 86% of the product, where the variables would accept about 66%. On the other hand, and you can see on the other side that the at the 50% point, which is 100.21 for the attributes data, it's actually a little bit 100.2125 for the variables type data. Okay, this is the AOQ curves that are compared, and you can see 100% inspection of rejected lots to AOQL, so the attributes data is 0.46%, where the variables is a little bit lower, it's a little bit tighter, 0.37%. So with a sample of size 5 compared to a sample of 80, we can make many more decisions early, and we actually have a tighter type situation. When we apply this to the recent 20 lots, now looking back over the data, and we then decided, based on the measurements that we had taken, okay, we'll use the first 5 measurements. So now this is the check on the data. I went back to the 20 lots, and I said, okay, if we had taken the first 5 measurements from those lots, what decision would we have made at that point in time? And we find that there were 4 means that would fall. So this is the average of the first 5 data points of the 20 batches that we had used to measure the process before. And there were 4 batches that were below 100.2125. So that meant that 4 batches out of 20 would require the typical IQC attributes sampling of 80 measurements. That would be a reduction of 80% in the batches needing extensive inspection. And also the 16 batches with means above 100.2125 would be accepted based on sample sizes of 5, and that reduced the sampling that they had, measurements that they had to make by 94%. That was a significant reduction in the process requirements in the IQC department. They have been applying that for over a year now, and they've had nothing but very good results from this. And now we're trying to carry this out onto the vendors to have them do it and reduce their cost to us in order to do this inspection. If we look at two-sided limits, everything is basically the same. We estimate the pool standard deviation from recent lots. We determine the AQL means, upper and lower now. And then we determine the rejectable quality levels, upper and lower also. We specified the producer's risk and the consumer's risk. And we determine what the sample sizes are now based on these formula over here. And you can see that the formulas, the only difference in the formula is that the alpha is divided by 2. The beta is retained at the same level. And when we determine the K upper and the K lower by the 2 formulas on the bottom, and in the plan, if the mean is between the upper and lower spec limit, the batch passes. If the mean of n items is outside those limits, we will reject the batch. And if you reject the batch, again, you go to the original sampling plan. So apply this to this problem over here. Again, talking about the X dimensions, we went through this calculation before, and we found out that 100.213 is slightly different from what we had before. Okay, and the upper spec limit in this case was 100.65. And we determined the rejectable level for 100 point, that point. And then, again, we're going back and find out what the rejectable quality levels are for these 2 situations. And basically, this is the same step that we did on one-side distribution. We're now doing it on 2-sided distributions. Okay. Found out what the rejectable level is now for upper. And we had found out what the rejectable level was for lower, and we found out what the acceptable level was for upper, and the acceptable level was for lower. And then we plug it into the formula, and the formula shows now that we should have approximately 7 units instead of 5 when we're dealing with a 2-sided spec limit, and that the KU and the KL are 100.211 and 100.589. So again, the plan, if the mean of 7 items is below 2.11 or above 100.589, we're going to accept. If the mean is outside these limits, we're going to reject the batch. If it's between those limits, we'll accept the batch. Now here's, just to portray what we had gone through with the single-sided, we're now doing it on double-sided. You can see that the distribution can vary between the upper and lower spec limits. And if your upper distribution approaches the upper curve, you have a certain percent that can fail. That's your AQL. Those haven't changed. Those are based on the original attribute sampling plan. And we can have the same situation on the lower sampling plan. And we have over here now, we have to indicate the risks associated with this. The difference, as I say, is the alphas have now become alpha over 2 because you have the probability of rejecting it on either side. Now, why beta instead of beta over 2? Well, because most likely if you're rejecting, it's going to be rejected on a one-sided type case rather than a two-sided type case. You have to think about that a little bit. It caused me some concern at first when I saw the formulas, but when I thought about it, if your distribution were wide, you can reject on both sides. But if you reject, the probability of accepting bad product, it's generally going to be on one side of the distribution. And that's why we kept a beta at even. At the same value as before at 10%. Okay, and again, this shows the beta risk. As I say, most likely if you're probability of rejecting it, you're going to be on one side of the distribution, so you put your beta on either side, left or right, from upper and lower. This is another way of looking at the data. This is in terms of your incoming batch means. And basically what this is saying is, as long as my batch means fall within those the black curve, I'm going to end up accepting the product, and the probability of acceptance gets smaller and smaller as I go closer towards the spec limits. And this is the plan with the variable sampling plan. This is now terms in the probability of acceptance rather than the defect levels. And you can see it's just a nice little curve that basically shows you, as long as my K values that I measure, the averages that I measure for 7 data points falls on that red curve inside there, then I will be satisfying the requirements that I had originally. Again, we applied this to the recent 20 lots, took the first 7 measurements of the recent 20 lots. That's this curve shown over here. 4 means, again, and that happened to be that fell below the, that were inside, outside the specification limits of the K-value that we had used. So that reduced our attribute sampling inspection by 80% of the batches, and it reduced the sample size that we had to take a look at of approximately 91%. So variable sampling plans that are based on the measurements rather than simple count of the data of rejectable parts, they can provide equivalent or better protection compared to the attribute sampling plan, and are based on assumptions that need to be verified for each CTQ, and can significantly reduce sample sizes, time, and costs for IQC inspection. Okay? Any questions? Yes.
Yes, Ron Andrews from Boston Law.
Yeah.
Does this variable sampling plan correspond to, I think it's ANSI Z1.9?
Yes, it's right. It's the same thing as the variable sampling plan. You'll say it was formerly one of the mill standard type documents, I think 404 if I remember correctly. But the difference between this one and that one is the fact that many of the military plans and the ANSI plans make your sample size choice depending on the incoming lot size. We're treating this as a process, a stable process, and we don't feel the need to try to adjust the sample sizes based on the sizes of the incoming lots. One of the issues that I continuously fight with at some of the procedures that are devised by engineering is that they would like to take sample sizes based on the size of the incoming lot, like they'll say 2% sample. And so we end up with varying OC characteristic curves, which is just no good for trying to get a consistent process going in there. So I always try to switch them from, like, instead of a 2% sampling, we have batches, for example, that can vary in size from 30,000 down to, a few hundred. Well, what sense does it make to take a 2% sample out of a sample size of 300 and compare it to 600 pieces or so from some other lot? So the difference between this is the assumption that we're dealing with what we call type B sampling, that we're dealing from a process. Other questions? Yes?
So I'm interested in what happened with the truncated data. When you move to a derived quantity instead of direct measurements, did the truncation disappear?
Actually, we're working on training the technicians not to do the truncation. And what we feel is that some of that is actually due to the supplier providing us with the truncated type data. Since we've been able to get these measurements done and actually a little bit more consistently now, can we be more careful with some of these measurements? We've actually improved the process, and we're getting fewer and fewer instances of the product getting close to the specification limits. I had one interesting example, by the way, when I was at General Instrument, and we had similar requirements on our suppliers that they provide us with the data that showed the distribution of the product coming in. And one day, the statistician came up to me and he said, "Dave, take a look at this." And the distribution was literally cut by a quarter. And we called up the supplier and they said, "What did you do? Why did you do that?" And he said, "Well, we had another customer that wanted that part of the distribution. So we sent them that and we gave you the rest." And I said, "No, that doesn't work out that way. Thank you." Other questions? Yes?
So I understand you use the pool standard deviations to estimate your overall sigma.
Right.
So could you talk a little bit about the assumptions that you're using means and what happens if your incoming material standard deviation changes? For example, if they have an excursion.
Well, that's the beauty of this process, because you're collecting data on samples of size 5. So all you do is keep measuring that over a period of time. You can measure the variance of those incoming and compare it to your assumptions using control charts. And if you have a sample, a batch that has a wide degree of variability, then you notice that. And by the way, we have criteria on the standard deviation of the incoming lots too, because sometimes, and this is very rarely happening now, but it was happening before, we have bimodal distributions. coming in where they mix certain batches together. And you can spot that because the variance increases in that batch. So that's a good thing to be checking for in addition, to make sure that your process, you're always doing the control charts on those samples of 5 that are coming in anyway, but you're also checking the range chart or the standard deviations chart to make sure that they're not out of control too. And if you get that signal, then you go back and take a look at a little bit more samples to see, get more detail on that to make sure you don't have multimodal type distributions. Other questions? Yes?
How difficult is it to extend this to where you have different sources of variability? Can you model it, using sort of combined sources of variation? Because here you essentially just modeled the within batch variability.
I would think you'd have to know where the different sources of variation are coming from, and then model it separately, each different source. I mean, if we have 2 vendors that are providing different levels of variability in their process, we have to establish the standard deviation for each one of them. This is a product, for example, the plates are based on powder metallurgy. And a lot of automotive industry parts are based on this powder metallurgy type processes. These plates are actually stamped. They're stamped in a 160-ton press that stands about 3 stories tall. And they generate these parts about every 15 seconds. They put powder in a little die, and then down comes the press at 160 tons and stamps them out. And then they're sintered and oxidized and so forth to make almost like a metallic structure, a solid type structure. If you have different processes that companies use, some, for example, some are double stamping it, some are single stamping it, then you might get different variability, in which case I would treat them separately unless I had indication that the variation that was between them had been reduced. Did I answer your question?
I think so. I'm thinking more along the lines, and maybe because I'm in a slightly different industry, where you have something where you cannot control it or separate it out, sort of like a noise variable. Mm-hmm. Maybe you have a destructive test and you know that your analysts measure things separately. Can you extend that estimate of the variability to encompass all those sources?
Yeah, that's what I say. I think you can using the control chart type approach and measuring the variability. And if you have defined differences, then separate them out, treat them separately. Another question? Yes?
Yeah, question. This is about your experience. If it fails the variable sampling plan, and then you go to attribute, and it fails that, in your experience, then they test 100%?
Yeah, right. They have to test 100% of the product to make sure that they've screened out the reject levels. And again, that's based on an assumption that they can live with some CTQs that are slightly out of tolerance, but they can't live with a lot of them. That's why they set the defect levels at where they are. Other questions? Okay. Well, thank you very much for your time.